So we've looked at all the directions, the right-hand rules. We're going to be using those right-hand rules to get the directions for all of the forces, because force is a vector. But now we're going to start to calculate the magnitude. We're going to start off by looking at the force on a single moving charge, proton, an electron, or some charged object. So if there is a force on moving charges, remember our symbol for a magnetic field was a capital B, because M is taken by mass. We know how to find the direction, right-hand rule. How do we calculate the magnitude? Well, here's your first equation. The magnetic force, and my symbol for magnetic force is F with a little subscripted B. Clay's going to open his eyes. That's a long blink. It's equal to the size of the charge, Q, times the speed that it's moving, that's a lowercase v, times the size of the magnetic field that it's in, QVB. QVB. Oh, hang on. Except it turns out the velocity and the magnetic field have to be at right angles to each other. Really, a charge experiences a force when it crosses the lines of a magnetic field, not when it's traveling parallel to a magnetic field. It's when it crosses the lines of a magnetic field. Sometimes the charge perpendicularly to the magnetic field. If that's the case, then you could find the component. It ends up being sine theta. So sometimes you'll see this written as F equals QVB sine theta. If theta is 90 degrees, which is what we want, the sine of 90 is 1, and you get QVB. If theta is 0 degrees, so they're parallel, the sine of 0 degrees is 0. So if they're parallel, you get no force. The charge will just travel in a straight line. Okay? Having said that, parallel is fair game. I may, Manny, give you one question where the charges are going in the same direction, parallel to the magnetic field, and then the answer is, oh, it's going to go in a straight line. I'm not going to ask you any of the component-y ones, though. On your test, I'm going to have everything at right angles. I've flogged components this year enough. So, the maximum force is experienced when the particles move in a direction that's perpendicular to a magnetic field at right angles. Example 1. A proton moving at 1.7 times 10 to the 6th meters per second enters a 0.15 Tesla magnetic field at right angles to the field. What's the net force on the proton? Let's call that part A, and let's call part B, what's the net acceleration? Spencer, what does part A want me to find?
The net force.
Okay, so it wants me to find a force. What's causing the force? The magnetic field. So it wants me to find magnetic force, FB, which our new equation says is equal to QVB as long as the velocity and the magnetic field are perpendicular to each other. Spencer, are they perpendicular to each other?
Yes.
Does say at right angles. Okay. Okay, then it's plug and chug. Q. It's a proton. 1.6 times 10 to the negative 19. V, velocity or speed. Well, velocity, I guess we're back in force as a vector. What's the velocity, Spence?
1.7 times 10 to the 6.
B, magnetic field in Teslas. And I get a force of 1.6 times 10 to the negative 19 times 1.7, scientific notation button 6, times 0.15. I get 4.08 times 10 to the negative 14. And it's a force newtons. Now that might not seem big. It's massive. It's massive. Alex, what does part B want me to find?
The net acceleration.
What did I find in part A? You know, it'd be cool if there was an equation that had force and acceleration in it. You look like you know of one. What's the equation that has both force and acceleration in it? The one from Physics 11. The one that technically should be right on your fingertips. Oh. And you even said F net, which means this will give me the net acceleration. Oh, how would I get the A by itself? A is going to be the force divided by m. The force is 4.08 times 10 to the negative 14. The mass, it's a proton. That's charge. Thank you for playing.
1.67.
So if I take this number and I divide it by 1.67 times 10 to the negative 27, I get a massive acceleration.
Damn, is that fast?
Okay. If it was a speed, but it's not, it's an acceleration. Yeah. Patience. Great question, but patience. Okay. In fact, I think we'll talk about the direction on the next page. Yeah. Okay. This is Mr. Dewick doing a hideous hand sketch. Okay. First of all, I'm asking you, so consider an electron as follows. Now, we don't deal with electrons. Which way is this electron traveling? To the right. Our right-hand rule doesn't work for negatives. So an electron traveling to the right is the same as a proton traveling which way? Left. And then I quickly scratched out an external magnetic field. What direction is that magnetic field? What do those X's mean? Is it out of the page or into the page? Okay, tail feathers of an arrow retreating from you into the page. The dot is the arrow coming out at you, and that's how people have remembered it for years. So the electron traveling right, all of you point your right thumbs to the left. Magnetic field is which way? Into the page. First of all, don't have a crick in your face. High five, okay? So point your hand into your paper. Which way will the electron be forced? Okay, watch. So when this electron gets here, it's going to feel a force down. It's going to feel a force down. So now it's traveling in that direction. All of you, an electron traveling down and right is the same as a proton traveling which way? So point your right thumbs this way. Which way is the magnetic field? Into the page. Which way will it experience a force now? Well, now, so it's going to experience a force this way. So it's going to get bent like that. And then it's going to get bent like that. And then it's going to get bent like that. And then it's going to get bent like that. In fact, it will be forced into a, what shape is that? Circle. By the way, this is why the Large Hadron Collider, this is why all those particle accelerators are circular. Because the charge will want to move in a circle naturally. So, are you ready? What path is this charged object tracing out?
Circle.
That means that I can say magnetic force is what's pushing me in a circle. And this is nice review from the very end of the year, too. The magnetic force is equal to QVB. Circular force was equal to, well, Alex, don't write this next bit down. You said F equals ma, so circular force is X equals mac. But what's our equation for circular acceleration, centripetal acceleration from our formula sheet? Or you might even remember it. Well, there's two. Clay, there's two. You know what? Do I have a letter V over here? I think I want the V here. So what is it?
V squared over R.
Sorry? Oh, and I guess, for what it's worth, one of the V's will cancel. Here's what this means, and this is one of the ways that they identify charged particles at particle accelerators. When they smash the particles together and the particles rebound off, they often have them go through a cloud chamber, which is like kind of like a film plate, and you'll pick up a radius of a circle. Well, if you know the radius, you can either find the object's mass, or you can find its speed, or you can figure out its charge, especially if you know how big the magnetic field that you're sending it through is in the first place. So let's look at some of this. Example 3. An electron moving at blah, 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 enters a perpendicular, so they are at right angles, it is going to feel a force, 5.45 times 10 to the negative 4 Tesla magnetic field, and traces out a circular path. What's the radius of this path? Jason, when you're done yawning, what does this question want me to find?
Radius.
This sounds circular to me. Oh yeah. Magnetic force is what's pushing me in a circle. And this answers your direction question. Magnetic force is equal to QVB. Circular force is going to be M4, sorry, not M4 pi squared R over T squared, MV squared over R. Looks like one of the V's cancels. There's one V on top on the left. There's a V squared or a VV on the right. Jason, what's this question asking me to find?
Radius.
How to get the R by itself? Yeah, I'm going to go times the R to that side and move those to that side. By the way, I like this question, I like this question, I like this question, but for some reason I see a lot of kids, they do this backwards. They move the MV to the bottom, and what they've solved for is 1 over R. They don't realize the R is starting out on the bottom. In other words, you're going to get R equals MV over QB. By the way, the top of that fraction, what is mass times velocity? Okay, so for what it's worth, just as kind of a nerd note, if you don't know the object's mass or velocity, but if you do know its momentum, you can also do some nice stuff. Or this gives you a way to actually calculate an object's momentum, even if you don't know its mass. Its momentum would be Q times B times R, if I move the QB back where it was. There's lots of stuff coming out of here. This is why the field of particle smashing of particle accelerators is so rich. Lots of good stuff here. Yeah, let's get the radius. R is going to be M. They didn't tell me the mass. It's an electron. I know it's 9.11, but I can't remember the 10 to the negative 31. V looks like it's traveling at 3.2 times 10 to the 7th. It's moving pretty fast. No, wait a minute. It's an electron. The protons in the Large Hadron Collider, I think they get them up to 99.999999% of the speed of light. So they get them hauling. All over.
Did we calculate how long it takes for it to go around? We calculated that, didn't we?
For what, where?
When we were doing the circular one?
I don't think we ever did we didn't really look at particle accelerators. We calculated period for satellites quite a bit. Hey, Q, charge. They didn't tell me. It's an electron. Do I want to put a negative in? No, radius by definition is positive. Radius by definition is a scalar, okay? So 1.6 times 10 to the negative 19. B is the magnetic field, which looks like it's 5.45 times 10 to the negative 4. What would the radius of this charged particle be? You get about 33 centimeters, 0.33 meters, 0.334.
I get the same.
Okay. Now this would allow you to predict a radius, but what's much more interesting is if you know the radius, you've measured that after smashing the particles together. They use cloud chambers and clever things that, so what happens in a cloud chamber, any charged object that travels through the cloud chamber leaves a white trail, almost like if you were painting with something, and it stays long enough that you can take a photo, and now you've got the radius. You can calculate the radius and work your way backwards and either calculate V or M or Q. Oh, and also Q and V in our electricity unit, in our parallel plates unit, you may recall, we have an awful lot of control over getting a charged object to whatever speed that we want, so we can really fine-tune a lot of these variables to find whatever's missing. Example 4. As shown in the above diagram, a proton entered a magnetic field at A. I wonder, is that right? Proton is traveling up the page. Point your thumbs up the page. What direction are those X's for the magnetic field? Into the page or out of the page? Into the page, so you can see, hey, yeah, that does work. The proton would get deflected sideways, would get deflected sideways, would get deflected. In fact, you can see the net force is always towards the center. It is centripetal. It is circular. Okay? Now, it'll end up going in a half circle and come back out. Unless we're clever, we can very easily keep it going in an entire circle too. You flip the current at the right time and you can do good stuff. They want the speed. Okay. What path is this proton tracing out, Vikas? That must mean that something is pushing it in a circle. Gravity? No. Magnets. Again, we'll end up with QVB equals MV squared over R. One of the V's cancels. Because what do they want me to find this time? How would I get the speed, the V by itself? What will I do with the M? What do I do with the R? Oh, okay. So if I hear you correctly, and I think I do, you're telling me it's going to be Q times B times R divided by M. Okay. Q. It's a proton. 1.6 times 10 to the negative 19. B in Tesla's 0.02, that's 2 times 10 to the negative 2, but that's less writing. R, 3.25. They didn't tell me the mass. It's a proton. 1.67 times 10 to the negative 27. Yeah. Okay, how fast did we get this proton up to? I get 6.23 times 10 to the 1, 2, 3, 4, 5, 6. No, yes? Yeah, 6.23 times 10 to the 6 meters per second. Yeah?
In the first equation, for QVB, there's no distance in there. Does that mean that every magnetic field everywhere in the universe is affecting every single charge everywhere?
Magnets extend out forever and ever and ever and ever and ever, but they weaken as you go further out. They weaken as an inverse square law. We're not going to look at the equation for magnetic fields over a distance. We're going to assume our magnetic fields are fairly close. And speaking of, let's carry on. That's for an individual charge. Well, if one charge feels a force, a bunch of charges in a wire should feel an even bigger force. Okay? So if we have a wire carrying current, once again, perpendicular to an external magnetic field, it will experience a force. The direction, this is that right hand, point your thumb in the direction of the current, high phi in the direction of the magnetic field, your palm points in the direction of the force, whichever way it is. It turns out the magnitude of the force depends on three things: the current, how much wire, the length, and the strength of the external magnetic field, how strong the magnetic field that it's in is. You can derive the equation for current by starting with the magnetic field on a single charge. The magnetic field on a single charge, magnetic force on a single charge, I said field, force, is QVB. I want to get rid of the Q. Well, if current, if I is Q over T, how could I rewrite this as Q equals? I think you're right, Kyle. Or Nick, somebody said it there. I heard. Oh, yeah. I thought you said I did? Yeah, IT. So we're going to get this. ITVB. And if you're going at a constant speed, which you are on a wire, if you're going at a constant speed, then D equals VT. There is no half AT squared because you're going at a constant speed. Hey, how could I write V with that? How could I get the V by itself? More specific, V equals? Kyle. Okay, so we get this. F equals, there's an IT, there's a D over T, and a B. Hey, what happens to the times? As an equation, here's how we typically write it. So the force, it's a magnetic force, so I'll call it FB, but this is on a wire. It's equal to B times I, and then to show we want the length of wire, typically we use a letter L. I'll always write mine lowercase, because if I write this, you're going to think that's B times I times 1. So, and in fact, I even think on your formula sheet, it's written as a lowercase loopy L, is it not? Or is it italicized? Oh, okay. Oh, except for this to work, the magnetic field and the current and the length of wire all have to be at right angles. Otherwise, your right-hand rule doesn't work. It requires 390 degrees. Okay. You can see it, though. D, L, length, distance. So find the magnetic force and the direction. So here's a wire. It's carrying 5 amps of current. The wire that's inside the magnetic field is 70 centimeters long, and the magnetic field, pretty big, 6 Teslas. Bill. BIL. Dale, what's the magnetic field?
5.
That's amps. I think that's current. What's the magnetic? 6? What's the current?
5.
What's the length? Don't say 70.
0.7.
Thank you. Double check. Are they all at 90-degree angles to each other? Yeah. Okay. So point your fingers, your right thumb, in the direction of the current. Which way is that magnetic field? Down the page. Which way will the wire feel a force? First of all, if you're multiplying it, it's going to be 30 times 0.7. 21? Is that right? No?
Yeah, no, it's not.
Yeah? Okay, so 21 newtons. But it wanted the direction. Which way will this wire feel a force? Now, if you find you're bending your hand weird, Travis, lift your paper up 90 degrees, and just that often is enough to unkink the what. So for me, boom, boom. You know what? The wire is going to get pushed into the page based on what I have here. Yes? No? Am I right? Thumb points to the right. Magnetic field on my screen is down the page. My palm is pointing into my screen, into the page. Okay? Or you could write, but I tend to just write it out. That's the symbol for into the page. Example 5. If the force on a 5 centimeter piece of wire carrying 12 amps is 1 times 10 to the negative 3 newtons, what's the magnetic field strength of the perpendicular field through which the current passes? What's this question asking me to find? Magnetic field strength. Which variable is that? I think you're right. Someone said it, I thought. B. Yeah, it's not I, that's current, not F, that's force. B. So I'll start out, good old F on a wire is Bill. What did you say this wants me to find? Get the B by itself. It's going to be the force divided by the current times the length. It's going to be the force 0.001, that is 1 times 10 to the negative 3, but that's less writing, divided by 12 times 0.05, 5 centimeters. And I get a magnetic field strength of 1.67 times 10 to the negative 3. No, yes? Yeah? 1.67 times 10 to the negative 3. Units magnetic field is measured in Teslas. The second last new unit that you'll ever use. Some cool applications of this. Any of you ever see the movie The Hunt for Red October or read the book?
I love that movie.
Okay. Here's the physics of the caterpillar drive.
I'll watch that.
Figured so. Okay.
That's a good movie.
So, magnetohydrodynamics is the use of magnetic fields to propel ships or submarines. The idea is you run a current through seawater. So you have to imagine, I couldn't draw this. Imagine, Clay, that there's a steel plate right here on the outside, and it's charged. It's charged in such a way that the current is flowing through the ocean water into the page, into the ship. Okay? So again, you've got to imagine that there's a plate right here. I had to take that away so you could see inside, but current is flowing this way. Got that? Then we have magnets. Where is the north pole of the magnet? Top? Where is the south pole of the magnet? Bottom. Magnetic field lines point from what to what? All of us, let's draw in the magnetic field lines. The magnetic field lines would look like this. So far, so good?
Those have no moving parts, right?
Ready? So, with this setup right here, which way is the current flowing? That's magnetic field lines. Which way is the current flowing?
Oh.
No. Read. It's in the question. Psst, look up. Which way is the current flowing? Okay, into the page. Back into the submarine, because the submarine's made of metal. Point your right thumbs into the page. Which way is the magnetic field pointing? Down. So if I go here, what direction will the seawater feel a force?
Back.
Out the back like a jet engine with no moving parts.
You know which way? No. Absolutely. I wonder what happened to the
Okay.
That'd be interesting.
There you go. There is your jet engine underwater with no moving parts. Now, there would still be some noise because anytime you cause water to move, there's cavitations and things. But what you wouldn't have are engine noises. Okay? So the premise of the novel, The Hunt for Red October, and the movie is that the Russians have invented this and the US can't detect their nuclear sub. And so they're worried that the submarine could surface right in New York Harbor, launch a nuke, and then duck underneath, and it goes from there. Read the book. I won't give you any more spoilers. But so you've seen the movie. There you go, Clay. There's the physics behind it. Really quite simple. It's a right-hand rule. Let's answer Josh's question. Josh said, Mr. Duick, how big are magnetic fields? So the magnetic field that we're actually going to calculate is the one from a solenoid. Okay? We're going to calculate the magnetic field that these put out. Specifically, we're going to calculate the magnetic field in the middle, right here, in which case the whole distance and radius thing won't play much of a role anyhow. And it'd be very, very close to the same magnetic field right on the end, right here, which is probably the business end if I'm trying to use it to do anything. So it'll be close. We need some variables. We're going to tell you that N is the number of turns of wire. If N is 1,000, that means you've wrapped the wire around 1,000 times. If it's a single wire, N is 1. L is how long the solenoid is. I is the current. B is the magnetic field that you want to create. So this is how you can create any size magnetic field that you want. Ampere determined, turn the page, that the magnetic field determined, created by a solenoid, depended on certain variables. He found the more current, the bigger the field. He said, I think I is on the top of the equation. He found the more turns, the bigger the field. He said N is on the top of the equation. Oh, but he found the longer the solenoid, the crappier it was. He said L is going to be on the bottom. In other words, he said magnetic field depends on N times I divided by L, except this won't give you an answer in Teslas. To get an answer in Teslas, we need to have a constant in front. The same way for gravity, we knew that gravity depended on big M, little m, and r squared. We'd put a big G in front to get an answer. Or for electrostatics, we knew that it depended on Q1, Q2, and r squared. We did a K. Here is the magnetic field of a solenoid. I'll put a vector on it, but we figure out the direction of the magnetic field using the right-hand solenoid rule. We hold the solenoid in our hand. Mitch, you with me? Okay. It's equal to mu0, that's the symbol. I had a British teacher in high school, one of my teacher heroes, and he always said mu0. And in his honor, and because that's how I learned it, you'll often hear me call it mu0, because a 0 is a naught in Britain. Times N times I divided by L. So mu0 is a constant, and it's on your formula sheet. Go find it.
Well, like, what is with the knot? Why is it there?
Can you first of all find the value of it? It's going to be in your list of constants somewhere there. So you don't have to memorize it. It's going to be right where K and where big G is.
4 pi times 10.
For what?
Pi.
What does pi have to do with... Because the universe seems to like the number pi. Okay. 4 pi times what?
10 to the negative 7.
And it's called... has one of the best names. It's called the permeability of free space. Kiowa, what did you learn in school today? Mummy, I learned all about the permeability of free space. Oh, Kiowa, you are ever so clever. Okay. 4 pi times 10 to negative 7. Problem. All of you, for the next few questions, every one of you must try these on your calculators, because some of your calculators will give you an error when you try typing this in. So follow along with me, and I'll have to show you a cheap workaround. But this is the number 4 pi times 10 to negative 7 that you have to put in front of N times I divided by L to get an answer in Teslas. You asked why mu0? I don't know. Or as you like, not? I don't know why not. Why?
That's a good one. So good on.
Nerd note, pi rears its head again. Okay? So if you want to figure out how big a magnetic field a solenoid will create, or if you know how big a magnetic field you need, you can figure out how many wraps of wire you need to put around it, how long your solenoid needs to be, and how many amps you need to send through it. There's a second version of this equation. Sometimes, instead of knowing the total number of turns, in fact, most of the time if you're buying a solenoid, they won't tell you the total number of turns and the total length. Instead, they'll take this and they'll just combine that in a ratio as turns per meter. Turns per meter. So the second version, which is also on your formula sheet, looks like this. Mu naught n, little n, times I, where n is big N over L in lowest terms. We need to practice some of these. Okay. Example 7. A solenoid is carrying 4.2 amps if the solenoid is 1.2 centimeters long and it's made of 750 turns of wire. What's the magnetic field at its center? Josh, what does this question want me to find? Yep. And in this course, the only equation to calculate magnetic field that I'm going to give you is for a solenoid. It's mu naught n times I over L. And this is what I want to write down, and you're all going to want to type this in because some of you might get an error. Mu naught is 4 pi, scientific notation, -7. N is the number of turns of wire. Travis, how many turns of wire have we wrapped around this solenoid? Yep. Travis, what's the current running through this solenoid? Divided by, what's the length of this solenoid? Don't say 1.2. On my calculator, I can go 4 pi, and I can hit my summation button, and I won't get an error. I think, Clay, on your calculator, if you go 4 pi, scientific notation button, -7, you might get an error.
Should I just do that first?
Yes. Try it, please.
No, I didn't get an error.
You did not? Same answer as me?
I'm working.
Okay. Who got an error? So even though the constant is written as 4 pi times 10 to the -7, you'll have to type pi times 4, 10 to the -7. Okay? And then you'll be fine. I'm pausing. You want to try this and get this answer.
If Max gets an error, that means my calculator is superior.
No, it means the software does calculations in a slightly different order, but it's pretty obscure. You have to combine a constant scientific notation and a coefficient. So, anybody not able to get that, now is your time to ask. Sorry? Like you're getting an error or not the right answer?
Saying an error.
So you're going to type times button, and then you're going to go for scientific notation, whatever that, -7 times 750 times 4.2 divided by 0.012. And it seems to be primarily seems to be the Casios. So it's got to be how their OS does that calculation.
3,007.
Then check your, is it -7? Anybody else? Worked now? Worked now? Worked? Worked? Who, Travis or Kohei? Okay.
The E is supposed to be there.
0.33 3 units magnetic field. Teslas. What if I wanted to double the magnetic field? I could either double the current to 8.4 amps, easy enough to do, we've just finished circuitry, or instead of 750 turns, I could wrap 1,500 turns, double the number of turns, or instead of having it be 1.2 centimeters long, I could make it 0.06 centimeters long. It gives us complete flexibility to really customize any size magnetic field that you want. Muck around with the numbers. Whatever size magnetic field you need, I can build a solenoid that'll generate that at its center. So it's really a nice electric device. Solenoid's hugely useful. I think last day we crossed out thousands of uses and I said millions of uses. This right here, the fact that you can customize a magnetic field. In fact, not only can you customize it, you can vary it because we know how we have the ability to change the current at a whim, so you can actually have a varying magnetic field as big as you want for this procedure, but then I want a same solenoid, but I want a bigger or a weaker magnetic field. Piece of cake. Example 8. Example 8, this was my attempt to do a 3D drawing. We're looking down the end of the solenoid. In other words, all of you imagine you're doing this. Okay, and that's why you just have the single piece of paper, or the single circle. I mean, you can sort of imagine, I guess, if you really want to go 3D, kind of that, but I just couldn't get that to work very well. It says, find the field and the direction in the center of the coil. The coil is carrying 10 amps of current, and it has, look, little n, 2,550 coils per meter. In this question, Dustin, what they've already done is they've gone that divided by that, and apparently in lowest terms, it's 2,550. This is the second solenoid equation on your formula sheet. The second solenoid equation, magnetic field, is mu naught little n times I. Again, especially those of you that had trouble with your calculator, try this one. It's going to be 4 pi times 10 to the negative 7. Little n is 2,550. I'm not saying that there's 2,550 coils on this wire. That would, on this solenoid, that would be if it was a meter long. If it's half a meter long, there's half as many coils. Or if it's a tenth of a meter long, there's 255 coils. All I know is that's the ratio of coils per meter, of turns per meter, and then times 10. Yeah?
How many turns per meter can you produce?
Good question. Conveniently, I have a video of the strongest magnetic solenoid on the planet. Patience. The answer is, with some cleverness, we can sort of do a calculus limit. We can almost make the coils into a solid if we're really, really clever. So that instead of single wires, you have an infinite number of patience. Anyways, let's get an answer here. 4 pi, scientific notation, negative 7, times 2550 times 10. And I get a magnetic field of about 0.032 Teslas. Anybody else? Is that right? Now remember, that doesn't sound big. That's pretty big. That's pretty big. Remember, 40 Teslas, I think, was the MRI machine video that I showed you. So 0.33 Teslas, that's a very strong magnet. This one here, still fairly strong. Strong enough probably to run an electric motor or something like that. 0.032 Teslas. It wants the direction. So we need to imagine that we're holding the solenoid. So if the solenoid is running into the page, I'm either going to hold my hand like this or like this. This is how I'm going to imagine holding the solenoid. I'm going to curl my fingers of my right thumb in the direction of the current. So if I do that, can I hold it this way? No. I must hold it this way. Yes? Which way does my thumb point?
On the page.
What direction is the magnetic field? Out of the page. North, coming out of the page. So if I wanted to draw the magnetic field, I would go like this. There's a magnetic field out of the page coming towards me. Is that okay? Put your pencil down, look up. A solenoid is to be wound on a cardboard form 30 centimeters long. So let's suppose you're a factory, okay? Company says, hey, we have room for 30 centimeters of length. Our circuit is providing 5 amps. We need a magnetic field of 6.28 times 10 to negative 3 Teslas. How many turns of wire do you need to put around that 30 centimeter long solenoid? So now you can start to customize and design. Okay. Well, the magnetic field of a solenoid is equal to mu naught capital N times I over L. Put the phone away. Okay, Trav, what's this question asking me to find? I'm going to even be more the number of turns of wire. Which variable? Yeah, N. N. How would I get the N by itself? What will I do with the mu naught and the I? And the L? So now we can really customize. Apparently it's going to be the magnetic field times the length divided by mu naught and divided by the current. It's going to be the magnetic field 6.28 times 10 to the negative 3. 0.3, right? Divided by 4 pi times 10 to the negative 7. 5 amps. How many turns of wire do we want to build into this if a customer has ordered this solenoid? How many turns of wire must we build into this? This should almost work out evenly. The reason I know it'll almost work out evenly, I cheated. The magnetic field, I think, is almost exactly 2 pi. So in theory, the pi's should come close to canceling. What do you get? You need to try these on your calculator. I'm hearing someone say 300. Is that right? Yeah? How, Travis, how long is this solenoid? So if I take that 300 and I divide it by 0.30 centimeters, I could either order a solenoid that had 300 turns, or I could say, give me any solenoid that's got 1,000 turns per meter. And that'll give me the same size magnetic field. So if they come back and they say, I only got 15 centimeters. Okay, in that 15 centimeters, I better have 600 turns, 1,000 turns per. Okay. That's what N means. I'd have to think about it. Do I need half? Maybe it's half. Okay, but that's what that lowercase n is, the number of turns per meter. So this solenoid would be rated as 1,000 turns per meter. What's your homework? Study for the test. Homework part 2 is enjoy your grad banquet. But I'm sorry, next week, Monday night or Sunday, because I see you Tuesday, you got some homework. Try number 1. Number 2. Three is good. I skipped 4. 5 is good. 6 is good. Never mind, skip 6. That's the one we just did as our example. Huh. Apparently I forgot to change the numbers when I copied and pasted it. 7 is good. Same question. 9. 10, 11.